Today I want to talk about one of my favorite results, which is that if you're to take two randomly chosen positive integers, the probability that their greatest common divisor is equal to 1 is 6 over pi squared. And this might look familiar to some of you because it's actually the inverse, or I should say the reciprocal, of the famous Riemann zeta function evaluated at 2. Another way to put this is that it's 1 over the sum of 1 squared plus 1/2 squared plus 1/3 squared, and so on and so forth. Now, before we get to the proof, I just want to mention that where I got this particular version of the proof is from the book Gamma by Julien Haville. It's a pretty good book. It's accessible to people who are in their undergrad still, perhaps have had a first course in calculus, and it talks about this mysterious constant that we don't even know if it's rational or not, and has a bunch of neat analytic number theory in it. Well, so with that out of the way, before we get to the main proof, we need to talk about the inclusion-exclusion principle and establish a generalization thereof. So in order to do that, we're going to have to travel to the Platonic realm. If you've had a first course in discrete mathematics or have done any sort of combinatorics before, even just some basic set theory, you've probably come across the principle of inclusion-exclusion. What this says is that the cardinality of the union of two sets A and B, that's going to be equal to the cardinality of the individual sets subtract the cardinality of the intersection. And we can see this pretty easily from a Venn diagram. If you were to count everything in A and everything in B, well, you would be double counting everything that lies in their intersection. And so that's why we have to subtract off that cardinality. Now, this holds for a union of two sets, but the question may arise, well, what if we have more than two sets? Is there some sort of more general version of this? Suppose now that I have three sets, A, B, and C, and I want to determine the cardinality of the union of A, B, and C. Well, we can draw, looking at this triple Venn diagram. Let's think about what happens if I add up everything in A along with everything in B and everything in C. Then what's outside of these regions that I'm shading is going to get double counted. So in particular, we can see that the intersection of A and B is going to get double counted, the intersection of A and C is going to get double counted, and the intersection of B and C is going to get double counted. So we should subtract off all of those intersections to prevent the double counting. So we subtract off the intersection of A and B, we subtract off the intersection of A and C, and we subtract off the intersection of B and C. But now we've taken away just a bit too much. So we've dealt with all of these regions. However, we've subtracted away the triple-wise intersection of A, B, and C. We're now missing these elements here. And so what we have to do is replace the elements that lie within the triple intersection. So the cardinality of A intersect B intersect C. Notice that there seems to be a continuation of a pattern here. In both cases, we're adding the singletons, and in both cases, we're subtracting the pairwise intersections. It's just that the difference between the union of two sets and the union of three sets involves, first off, subtracting more pairwise intersections, and then adding a triple intersection. One can carry this out for quadruple unions, and having all three of those examples would be would give you a pretty good handle on what the pattern might be in general. But I'm just going to write it out, the full generality right now. If you have a union of sets call them a sub I, where the sum is from 1 up to I, then the cardinality of that union is going to be the sum from I equals 1 up to n of the individual sets a sub I. It's then going to be, you're going to subtract from that the sum over all pairs I and j, of course going up to size n, of each of the pairwise intersections aij. So I'm using a notation here just to make things a bit cleaner. When I write a subscript ij, what I really mean is ai intersect aj. And in general, if I write I1 ... up to ik, what I really mean is I1 intersect I2 intersect ... up to intersecting with aik. Continuing on in the sum of cardinalities, I then go over all the triple intersections. And as you might have guessed at this point, this pattern continues, alternating sums, until finally one has reached the intersection of all of these sets in the collection. What we require now is a proof of this claim. And we're going to use the good old workhorse of basic discrete mathematics, the principle of mathematical induction. Well, we very clearly have our base cases already. And so what we have to do is assume that this formula holds for all unions of n sets and prove that it holds for any union of n plus 1 sets. So suppose I have a union of n plus 1 sets, a sub I. Well, this is equal to the union of the first n of those sets, a sub n, and then taking the union of the n plus 1th set. So here we can think about this as just a union of two sets, and we can apply the basic principle of inclusion-exclusion here. So what we get is the cardinality of the union from 1 to n of a sub I, plus the cardinality of a sub n plus 1, and of course we have to subtract the cardinality of the intersection of these sets. According to our induction hypothesis that the formula holds for all sets of size n, we already have our formula for the first term. So applying that, we have the sum from I equals 1 up to n of the cardinalities of each of the a sub I, subtract the cardinalities of each of the pairwise intersections, and then add the triples, subtract the quadruples, etc., until we reach the final term, which is the intersection of each of these pieces. We have the cardinality of a sub n plus 1 still, and we're subtracting from that the cardinality of. Now we can distribute the intersection through this union, and so what we're going to get is the union from I to n of the intersections a sub I with a sub n. This a sub n plus 1 term, we can absorb this into the first sum, because in particular we're trying to show that the cardinality of the union of all these sets, well, the first term of this should be the sum of the individual cardinalities. So I can rewrite this expression as the sum I equals 1 now up to n plus 1, and it's starting to look like the result we're trying to establish. Again, I'm subtracting the pairwise intersections, adding the triple-wise intersections, subtracting the quadruples, and so on. And now for the last term, again, this is now just a union of n different sets. And so by our induction hypothesis, we can apply the principle of inclusion-exclusion. So what we obtain then is the negative of the sum first of the individual cardinalities a sub I intersect a sub n, subtract the cardinalities of all the pairwise intersections. But now, notice that a sub I intersect a sub n. If we were to intersect that pairwise with another one of these terms, say a sub j intersect a sub n, well, this double intersection of a sub n is redundant. So we can really just write this as a sub I intersect a sub j intersect a sub n. So the second term is really just the triple-wise intersections, all involving a sub n. And so on and so forth. Plus, minus these sums. So what we see happening in this final term is that we have the pairwise intersections involving a sub n, the triple-wise intersections involving a sub n, and these are exactly those things that are missing from the final formula that we're trying to obtain. So we can combine these together and get that we have the sum from 1 to n plus 1 of the individual a sub i's, subtract, and now since this minus sign is distributing into these brackets here, we're also subtracting off all the pairwise intersections involving a sub n. So that can now get absorbed into the term of the pairwise intersections, and so now it's all the pairwise intersections going up to the indices n plus 1. Likewise, for the triple intersections, we now have the addition of the I, j, k of the triple intersections. This time, the indices all going up to n plus 1, minus, plus, and it keeps going. And this is precisely the inclusion-exclusion principle for n plus 1. Therefore, using the principle of mathematical induction, we've established the result. Before getting to the main proof, we just need one more quick lemma, which is about expanding a certain infinite product. So suppose the infinite product of 1 minus xi converges when the xi are just some real numbers. In other words, we can expand it out as 1 minus x1 multiplied by 1 minus x2, and so on and so forth. Well, first we distribute the first term into the parentheses involving the x2 term, and what we get is that 1 minus, we have 1 minus x1 minus x2 plus x1 multiplied by x2. And to the right, we still have the term 1 minus x3, and so on and so forth. Now we distribute this new term into the term involving 1 minus x3, in which case we're going to get 1 minus x1 minus x2 minus x3, and then we're going to add the multiples of each of these. So we'll have positive x1, x2, positive x1, x3, positive x2, x3, and finally we'll subtract off the triple product x1 multiplied by x2 multiplied by x3. And all of this is going to be multiplied by 1 minus x4 on the right, and so on and so forth for the higher terms. So we can see this pattern here, and it's actually very similar. It's a related result to the principle of inclusion-exclusion, where we have 1, and then we're subtracting the singletons, if you will, then we're adding the doubles, subtracting the triples, and you can see that this pattern is going to continue, so that ultimately this is equal to 1 minus the sum from I equals 1 up to infinity of xi plus the sum over all distinct I and j of xi multiplied by xj and minus plus so on and so forth. We're now prepared to tackle the main question at hand. That is, what is the probability that two randomly chosen positive integers have GCD equal to 1? And we're trying to show that this value is 6 over pi squared, which is actually 1 over the value of the Riemann zeta function evaluated at 2. Now, we're dealing with an infinite set here, and we're thinking about grabbing arbitrary elements from an infinite set. So one thing we can do where probability is a bit easier to understand is first work on the finite realm. So suppose we have some positive integer n, some natural number capital N, and, well, we want to know how many pairs of integers have GCD 1 which are less than or equal to n. So I'm going to define the following sets. A is simply going to be all the pairs of integers. And of course, there's exactly n squared of these. So I'm using this hashtag to mean the cardinality of the set. I just find it's a little nicer to use instead of the absolute value bars that sometimes get used in these situations. So in order to see this, of course, well, we have n choices for a first number and n choices for the second number, so altogether there are n squared choices. And secondly, I'm going to let the set capital pi sub n, this is going to be a subset, being those pairs such that, of course, again, they are, both numbers are between 1 and n, but now we're supposing that the GCD of a and b is equal to 1. And we know then that the probability that some pair of integers are relatively prime, given that they belong to the set, I should call the set A sub n. So, given that they are between 1 and n, well, this is much easier to deal with. This is just finite probability. So this should just be the cardinality of the set capital pi sub n over the set capital A sub n, the cardinality of this set. It stands to reason then that if we know all of these, if we can compute these finite probabilities, then what we're looking for should just be to take the limit. That is, the probability that any two randomly chosen integers have GCD 1, this should be equal to the limit as n approaches infinity of the cardinality of capital pi sub n over the cardinality of A sub n. Now, determining the cardinality of A sub n, this is something we've already achieved. We know that that is n squared. The problem then is to determine what the cardinality of pi sub n is. Well, one way we can do this is realizing that pi sub n is a subset of A sub n. So one way we could perhaps count the cardinality is recognizing that A sub n is going to be the disjoint union of the complement, the set theoretic complement of pi sub n with pi sub n. So this dot above the union means that it's a disjoint union. So perhaps it might be easier if we can determine the cardinality of this set, because if we have the cardinality of a sub n and the complement of pi sub n, we can then determine the cardinality of pi sub n. Let's think about what this means. Pi sub n is the collection of all pairs of integers that do not share any common divisors. So pi sub n complement should be all of those pairs of integers which do share some common divisor. So in order to describe this set, I'm going to first describe one more set. I'm going to call this p sub n. And this is going to be all the list of primes, p sub 1, p sub 2, up to some p sub n, where each p sub I is less than or equal to n itself. We're now going to construct sets b sub I, where these are going to be pairs of integers a and b, where a and b, again, are both between 1 and capital N. But now we're going to have the extra condition that p sub I divides both a and b. And the reason for making this definition now is that we can describe our complement of capital pi sub n in terms of these b sub I. So recall that the complement of the pi sub n should be all those pairs of integers which are divisible by some number which is between 1 and n. Well, we've listed all the prime numbers between 1 and n in our set p sub n. So if any number is going to be divisible by something less than n, it's certainly going to be divisible by one of these primes. So if some pair is divisible by some number, it must fall into one of these sets b sub I. In other words, the set capital pi sub n complement, this has to be the union of all the b sub i's. Okay, so recall our goal is to find what the cardinality of capital pi sub n is. Now, since we have a sub n written as this disjoint union of sets, that means that the cardinality of a sub n is equal to the cardinality of capital pi sub n complement plus, and it's important here that we have this disjoint union, meaning we can just add the cardinalities of sets, plus the cardinality of pi sub n. And this is the quantity we want. The cardinality of a sub n we already know to be n squared. And the whole reason for setting up these b sub I is now we can use our principle of inclusion-exclusion, and hopefully by determining what the cardinalities of the b sub i's and any of their intersections are, we'll be able to determine the cardinality of the entire union, and that will help us figure out the cardinality of pi sub n. So recall the principle of inclusion-exclusion. This tells us that the cardinality of the union of all the b sub i's, this should be equal to the sum of the cardinalities of each of the b sub i's minus the cardinalities of each of the intersections of the b sub i's. Then we need to add back in the cardinality of the triple intersections, and so on and so forth. So then the question becomes, can we determine what each of these cardinalities are? Well, let's consider the following. Suppose I have some little n, some natural number, and I list the multiples of n. So I have 1 times n, 2 times n, 3 times n, and it keeps going, and eventually I must hit some number m so that m is the largest integer such that this is still less than or equal to capital N. Another way to see what this is saying is that if we were to take the floor function of n, capital N, divided by little n, this should equal m, right? Because this is the exact number of times, or the largest number of times that n can fit into capital N. In other words, this quantity is equal to the amount, the numbers, A, let's call them, which are less than capital N and such that n divides A. Because remember, this is counting all the multiples. So each of these numbers are, by definition, divisible by n. So what that means for us is that the cardinality of the set B sub I, well, we know for one such number, the B sub I, these contain pairs of integers, A and B. So how many choices do I have for my A, for the first number to be divisible by the prime P sub I? Well, given by the calculation we just made, I should have capital N divided by P sub I choices. On top of that, there should also be capital N over P sub I floor function many choices for B, which are between 1 and n and divisible by P sub I. So overall, there's the square of the floor function of capital N divided by P sub I, many choices for numbers which are pairs of integers which are between 1 and n, and both share a common divisor, P sub I. What about the double intersections? Well, in this case, we want to know about pairs of integers that are divisible by two of the prime numbers. So if some number is divisible by two prime numbers, it must be divisible by the product of those two prime numbers. So what we're really counting then, again using the same argument with the floor function of capital N over lowercase n, is this count should again be n divided by now P sub I times P sub j, floor function. That counts our choices for A. And then we have, again, that many choices for B. So we have capital N over P sub I, P sub j, floor function squared, many choices for pairs of integers having the divisors, both having the divisors P sub I and P sub j. And in general, you can see that this pattern is going to continue, so the n-ary intersections is just going to be the choice of that many prime numbers in the denominator. Thus, our formula that we obtained from the principle of inclusion-exclusion tells us that the cardinality of the union of the B sub i's should be the sum over all prime numbers of first the cardinalities of each of the B sub I. Well, the cardinality of each B sub I we figured out was capital N divided by the prime that it corresponds to, P sub I. And we took the floor function and squared it. And then we subtract the sum over all pairs of primes, where we found the cardinality of the double intersections to simply be n divided by the product of the corresponding primes, then applying the floor function and squaring, and we continue for triple intersections, quadruple intersections, etc. Therefore, looking back at our formula, n squared equal to the cardinality of the union of the b sub i's plus the cardinality of capital pi sub n, we obtain that pi sub n is equal to n squared minus the cardinality of the union of the b sub i's. And from the work that we just did, it's the negative of the expression we found for the cardinality of the union of b sub i's. We obtain the following expression. And now, if I divide both sides by n squared, on my left-hand side, I'll have the cardinality of pi sub n divided by n squared. And recall, it was this exact expression that we wanted to take the limit of as n approaches infinity to obtain our result. So we're getting pretty close. On the right-hand side, n squared divided by n squared, of course, is 1. And distributing the 1 over n squared into each of the remaining sums, I get this expression. Well, now we want to evaluate the limit as n approaches infinity. What we're going to need to do in this case is figure out, well, we have these terms, 1 over n multiplied by the floor function of n over x for some term x. So this happens here. Well, we're taking the square of this, but it's happening here. Our x is any of the p sub I. Here our x is any of the p sub I times p sub j. So we need to figure out what the limit is of this expression when n approaches infinity. Remember that the floor function rounds things down. So 1 over n multiplied by n over x, rounded down, this is certainly going to be less than or equal to 1 over x multiplied by n over x, and those n's just cancel to give us 1 over x. On the lower end, we know that this must be at least the size of 1 over n multiplied by n over x minus 1. Because the floor function is the nearest integer smaller than n over x. So certainly n over x minus another integer entirely is going to be smaller. This expression can be rewritten as 1 over n multiplied by n over x minus 1 over n. And the n's cancel out. So we're left with 1 over x minus 1 over n. And this is less than or equal to 1 over n over x, which is less than or equal to 1 over x. Now I can take the limit of these inequalities as n approaches x. What I find is that this limit, well, if we look at the limit of 1 over x as n approaches infinity, that's just 1 over x. There's no dependency on n whatsoever. If we look at the lower end of things, well, the limit of 1 over n as n tends to infinity is just 0. The only other term, again, is 1 over x, and that's unaffected by the limit as n approaches infinity. So we get 1 over x. Thus, we see by the squeeze theorem that the limit of 1 over n multiplied by the floor function of n over x as n approaches infinity must be 1 over x itself. applying this limit to our expression, we get that the limit of the cardinality of pi sub n over n squared is equal to, now recall x squared is a continuous function, so we can push limits inside. So this becomes 1 minus the sum over each of the primes of of 1 over p sub I squared plus the sum over the every pair of primes 1 over p sub I p sub j squared minus the triples and the quadruples and so on and so forth. And now these sets here, the p sub n, are actually infinite because we've taken the limit as n goes to infinity, so the set p sub n contains all the prime numbers. And this should look familiar to one of the other little lemmas that we proved. So just so you recall, it was that just so you recall, it was that 1 minus x1 plus x2 plus ... plus the products of each of the terms, x1 times x2 plus x1 times x3 plus ... minus the triples plus the quadruples, etc., resulted in the product 1 minus x1 multiplied by 1 minus x2 multiplied by 1 minus x3, and so on. We obtain the product, so keep in mind this capital pi here simply means an infinite product over all prime numbers. It has nothing to do with the capital pi sub n over here. So this is the infinite product over all prime numbers of 1 minus 1 over p squared, where p is the given prime number. Rewriting this a little bit, we can see that this is the same thing as p squared minus 1 all over p squared, which is the same thing as, so I want to invert this term. So this is going to be 1 over the product, and this means I have to invert now each of the individual terms. So this is going to become 1 over the product over all primes of p squared divided by p squared minus 1. And again, I'm going to now factor out a p squared from the numerator and denominator. So I get the product over all prime numbers of 1 over 1 minus p to the negative 2. And finally, it's this term in the denominator that you should recognize as the Euler product formula for the Riemann zeta function. So the Riemann zeta function at S is defined as the sum over all integers of 1 to the s, which is the same as the product over all prime numbers of 1 over 1 minus p to the negative s. Therefore, our limit, the limit as n approaches infinity, of the cardinality of pi sub n over n squared, which we determined to be the probability, that two arbitrarily chosen integers have GCD equal to 1. This is equal to, looking at our rightmost term of this limit expression, is 1 over the Euler product for zeta evaluated at 2, and by the famous Becel problem, this is 6 over pi squared.